Hi, so today will be a quick introduction to number theory, and we will be doing some problems along with it. So firstly, what is number theory? So number theory is the study of the integers. So some notation you'll see used in problems can be as follows. Notation. So you'll see this n being used a lot. If you see this n being used, this refers to the set of the natural numbers. If you see the n along with the 0, this would just mean natural numbers along with 0. So you can say the non-negative numbers. Non-negative numbers. If you see the c being used, this will refer to the set of the integers. So when we say natural numbers, so that would be 1, 2, 3, 4, on and on. The natural numbers along with 0 would be 0, 1, 2, 3, on and on. The integers would be the negative numbers as well, so -2, -1, 0, 1, 2, on and on. So some other notation you'll see this rounded e being used, and it means elements of. So if you see x elements of n, that just means x is a natural number. You'll also see this flipped e, and this means there exists. So you may be asked to prove that there exists x part of the z such that something is true. So in other words, we should prove that there is an integer x so that some or other statement is going to be true. Then you will also see this flipped a being used, and this means for all. So you may see a question that says, prove that a certain statement is true, prove that this is true for all x, y part of the integers. So you have to prove some statement is true for all integers x and y. Okay. You'll also see these arrows being used. So the forward pointing arrows, this means implies. So you may see statement A implies statement B. So whatever this statement says, from this we can conclude that this statement must also be true. You'll also see these arrows used, so pointing to the front and to the back, or pointing to right and to left, and this means if and only if. So you'll see statements A is true if and only if statement B. Or you can see it as statement A implies statement B, but statement B must also imply statement A. So both of them imply each other. Okay. So you don't have to use this notation in your proofs, but they can be quite useful. It can also be quite useful when you're reading proofs online and you want to know what is being said. Next, we're going to look at divisibility. You already probably know what divisibility means. So, so when A divides B, or A can divide B, that just means A can divide B without leaving any remainders. So you would indicate it as follows: A divides B. So with this line, this would be read as A divides B, or B is divisible by A. Also taking note that when we use this notation, it's where A and B are integers. So we won't use this for real numbers, for example. You can also see this as there will exist some integer m such that B will be equal to MA. So let's look at an example quickly. So say 3 divides 12. In other words, 12, this is true because 12 is equal to 4 times 3. So in this case, you can see the m is equal to 4. So this is the m, 12 is the b, 3 is the a. Okay, now we're going to look at some properties of divisibility. Properties. Okay, firstly, 1 divides b where b is a integer. So 1 is going to divide every integer. Secondly, if a is not equal to 0, so a is also an integer, then that implies that a will divide 0 and a will divide itself. So some of these may seem pretty obvious, but it's still important to just know it formally. If a divides b, then a will also divide minus b, and minus a will divide b. Fourth property is that if a divides b and a divides c, then a will divide m, b plus nc, where m and n are integers. So how we would prove this is we could say, okay, b is equal to m1a for some m, so for some m1 integer, just like how we wrote it up here. So 12 is equal to 4 times 3, so we can rewrite b as in terms of a. C is equal to m2a. This means we can rewrite this expression as being equal to m1a plus n m2a, which when we factorize will be equal to m1 plus n m2. Okay, fifth property says that if a divides b and b divides c, then this implies that A will divide C. Once again, you can do it similarly as the fourth one. You can rewrite B as being M1A, and C is equal to M2B. And then we can apply that to that, and we will see that A will be a factor of C. Okay. The sixth property says that if A divides B, this implies that the absolute value of A will be smaller or equal to the absolute value of B. So when we talk about the absolute value, it's the distance. It can be seen as the distance of a number from 0. So if you have -2, you can say this will be 2. 2 will be equal to 2. So if it's a negative number, you take the minus away, the negative sign away. If it's a positive number, you leave it the same way. Okay, for the seventh property, we have that if A divides B and B divides A, this implies that A will be equal to plus minus B. You can try to solve this on your own. You have to use the sixth property. So with the sixth property, we know that this will be true, and this also means that this will be true. So now we have this and we have this, which means the absolute value of A is equal to the absolute value of B, in other words. Okay, eighth property. If M is not equal to 0, also M being an integer, and A divides B, then this implies, or this is if and only if, MA divides MB. So you can multiply an integer in, and this will still be true, and assuming this integer isn't equal to 0. Ninth property says that if A divides B and C divides D, then AC will also divide BD. We can once again prove this similarly. We can say B is equal to M1A, D is equal to M2C, and we can put that in, and we'll see that AC will be a divisor or a factor of BD. Okay. So let's quickly look at a problem using these properties. Okay. Okay, so they tell us let M and N be natural numbers, and let Mn plus 1 be divisible by 24. Show that M plus N is divisible by 24. So what they're giving us is that, so we know M1N is divisible by 24, so 24 divides Mn plus 1. We want to prove 24 divides M plus N. Okay, so firstly we can note that if, note that 24 dividing Mn plus 1, or 24 divides Mn plus 1, implies that 8 divides mn plus 1 and 3 divides mn plus 1. The reason we're taking 8 and 3 is because they are prime numbers. So we want to split 24 up into its prime divisors and look at mn plus 1. Okay, also note that to prove that m plus n is divisible by 24 would be the same as proving 8 divides mn plus 1 and 3 divides mn plus 1, or not mn plus 1, m plus n. Okay. What we're going to do is we're going to show that this implies that, so since 8 divides mn plus 1 and 3 divides mn plus 1, this means that 8 does not divide m and 8 does not divide n, as well as 3 does not divide m and 3 does not divide n. We know this since if one of them was to be divisible by 8, then this expression mn would be divisible by 8, but this wouldn't make sense since if you add 1, it would not be divisible by 8 anymore. The same can be said for 3. If mn was a multiple of 3, if you add 1, it would not be divisible by 3, and that would be a contradiction. So neither of these can be divisible by 8. If 8 does not divide m and 8 does not divide n, we can further say that 2 will not divide m and 2 will not divide n. So both of them will be odd, so odd integers, or odd natural numbers. Just going to write odd numbers. Okay. Now we're going to look at m squared minus 1. So m squared minus 1 is going to equal m minus 1 times m plus 1. We know this since there's a rule that says difference of squares is difference of squares says that if you have two numbers a and b, a squared minus b squared will be equal to a minus b times a plus b. And that's how we derive m squared minus 1 is equal to a minus 1 times m plus 1. Now, from this we can see that m squared minus 1, so note m minus 1 and m plus 1 will be two consecutive even numbers. This means that one of them will be divisible by 4. Or m plus 1 will be so we can quickly look at even numbers generally. So if you have 2, 4, 6, 8, 10, 12, on and on. So we know m and m minus 1 and m plus 1 are going to be two even numbers, two consecutive even numbers. And you'll see that one of them will need to be divisible by 4 and the other one will need to be divisible by 2. So this will then imply that m minus 1 times m plus 1, or let's rewrite the top sentence. So 4 will divide m minus 1, or 4 will divide m plus 1, which implies that 8 divides m minus 1 times m plus 1, since we already know the other one would also have to be divisible by 2. Okay, now we do something similar for 3. So once again, m squared minus 1 is equal to m minus 1 times m plus 1. From here on, we see that, is that correct? Okay, so we had 3 cannot divide m. So we already know that from over here. We already know this. This means that if we consider the numbers m minus 1, m, and m plus 1, one of them must be divisible by 3. So since there are 3 consecutive numbers and we already know m isn't divisible by 3, we know either m minus 1 or m plus 1 is going to be divisible by 3. So since 3 does not divide m, this implies that 3 divides m minus 1 or 3 divides m plus 1, which will imply that 3 will divide m squared minus 1, since m squared minus 1 is equal to m minus 1 times m plus 1. So 3 is going to be a factor of either this or this, and in other words, it's going to be a factor of m squared minus 1 as well. Okay, what we then do is, now that we've established that 8 divides m squared minus 1, so this was m squared minus 1, and 3 divides m squared minus 1, so since 3 divides, let's write 8 first, since 8 divides m squared minus 1, and 3 divides m squared minus 1, this must imply that 24 will divide m squared minus 1 as well. What we do from here on, we say that this must mean that 24 will divide m times mn plus 1 minus n times m squared minus 1. So we were already, in the question we were told, okay, this divides 24, and now we know this also divides 24. So we know this whole expression will also divide 24. You can look at the properties and you will see that this is true. But let's rewrite this expression now. This is going to be equal to m squared n plus m minus m squared plus n, which we can rewrite. So these are going to cancel out, and you will be left with m plus n. So we are left with 24 divides m plus n, which is what we wanted to prove. Okay. Okay, so now let's quickly look at the divisibility rules. So we've already done the divisibility properties. So these are properties are pretty much rules on how to do divisibility, how to use divisibility. The divisibility rules refer to the rules that one can use to predict whether a number will be divisible by a certain number, are not by looking at its digits. Okay. So if we want to know whether a number will be divisible by 2, we would look at the last digit. So we would see if the last digit is even. So if we wanted to know whether a digit is, or a number is divisible by 3, we would say the sum of the digits has to be a multiple of 3. Four would be last 2 digits, multiple of 4. So let's quickly look at an example. If we have a super long number like 5, 1, 2, 3, 5, 6, 8, 1, 2. Let's make the last one 6. So if we want to predict whether it will be divisible by 2, we look at the last digit. It is 6, and 6 is even, so it will be divisible by 2. If we want to see whether it will be divisible by 3, we can add all the digits, 5 plus 1 plus 2 plus 3 plus 5 plus 6 plus 8 plus 1 plus 6. That will be 6, 8, 11, 16, 22, 30, 31, 37. Let me just check that. 8, 11, 16, 22, 30, 37. However, 37 is not a multiple of 3, so this number would not be a multiple of 3. If we were to make this instead 5, then the sum of the digits would add up to 36, and it would be true. So 36 would be a multiple of 3. Okay, 6, looking at the last digits, multiple of 4. So only looking at the 16. 16 is a multiple of 4, so this number would be divisible by 4. Okay, 5, last digit is 0, 4, 5. Okay, so looking at this number, the last digit is 6. It is not 0 or 5, so this would not count. Now for 6, so if you think about it, if you say something is divisible by 6, it means it's divisible by 2 and it is divisible by 3. So we're going to refer to rules for 2 and 3. So we already said, okay, it is divisible by 2. However, we saw that it is not divisible by 3, which means since both of these rules need to be true for it to be divisible by 6, this would not be true. For 7, there isn't a very nice rule for 7. You can go look online at some more of the rules. Some of them, the rules for 7 are just a bit harder to remember, so I'm not going to cover it now. For 8, it would be the last 3 digits multiple of 8. So what you'll notice is for 2 we had the last digits, for 4 we had the last 2 digits, and now for 8 we have the last 3 digits. So you can maybe guess that for 16, the next power of 2, we would have the last 4 digits if we'd have to look at the last 4 digits to determine whether it would be divisible by 16 or not. Okay. Then the next one, oh, by the way, this number 816, 816 is divisible by 8, so this would hold. 9, sum of digits multiple of 9. So notice that for 3 we had the sum of the digits being a multiple of 3. Now for 9 we have the sum of the digits being a multiple of 9. We already said that the sum of these digits are going to be 37, which is not a multiple of 9. So for 8 was true, 9 will not be true. I'm not going to do 10, but you can do the same as you would for 6. So for 6 we looked at 2 and 3. For 10 we're going to look if 2 and 5 holds. So I'm not going to do that now. And so many other, there's like a huge list of divisibility rules for lots of the numbers. You can go onto Wikipedia, and there are some cool YouTube videos for it too. Okay. Okay. Next we're going to be looking at the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic states that every integer, or every natural number n, bigger or equal to 2 has an unique prime factorization. So what this means is every number can be written in terms of its prime. So let's look at, you could say n is equal to p1 alpha 1, p2 alpha 2, on and on until pk alpha k, where p1, p2 till pk are unique primes, and where alpha 1, alpha 2 to alpha k are, let's write this, are natural numbers. So let's look at an example real quickly. So one could say 12 is equal to 2 to the power of 2 times 3, or 3 to the power of 1. So in this case, you can say P1 is going to be 2, alpha 1 is 2, then P2 is 3, and alpha 2 is 1. Let's look at another one. 30 is equal to 2 times 3 times 5. So in this case, P1 is going to be 2, alpha 1 will be 1, since it's going to be to the power of 1 for each of these. P2 will be equal to 3 alpha 2 will be equal to 1, P3 will be equal to 5, alpha 3 will be equal to 1. Okay, now let's look at some rules that we can use in problems, or some lemmas. Okay, so every composite n has a unique prime divisor that is smaller or equal to n squared. So when we say composite, this just means not prime. So it's going to have 3 or more divisors, in other words. So this would be important. Okay, so why important? Checking. This is important when you're checking whether a number is prime or not, and you want to lessen your work. So let's say we had to check whether the number 2017 is prime. So if we wanted to check whether the number 2017 is prime, which it is, we'd have to check, or you'd think we'd have to check all of the prime numbers going from 2, 3, 5, 7, 11, up till 2017, which is a lot of work. But this rule says that if 2017 is composite, so if it is not prime, if 2017 is not prime, it will have a prime divisor that is smaller or equal to the square root of 2017. So let's look at the square root of 2017. So the square root of 2017 is going to be around here. So bigger than 44, but less than 45. In other words, we know there is going to be, if we want to, instead of checking all of these primes, we can limit our primes to being 2, 3, 5, 7, 11, up till 41 and then 43. Instead of checking all of these, we can only limit it to them, which is still quite tedious, but way less work. Another quick fact is that 2021 is equal to 43 times 47. This is important because I like to ask questions surrounding the year number in Math Olympiads. So do remember this. You can also remember it by the fact that 2021 is the difference of squares. So it's 2025 minus 4, which is going to be 45 squared minus 2 squared. In other words, let me go down. In other words, it's going to be 45 minus 2 times 45 plus 2, which is where we'll get 43 times 47. Okay. Now looking at another rule. Okay. So remembering that we wrote n as being equal to this, according to the fundamental theorem of arithmetic, we can say that n will have alpha 1 plus 1, 2 plus 1, up to alpha k plus 1 prime divisors, or divisors, not prime divisors. Divisors or factors, if we want to say that. So let's look at an example. Say n was equal to 12, so we had 12 equal to 2 to the power of 2 times 3. So now 12, okay, so looking at the divisors of 12, divisors would be 1, 2, 3, 4, 6, and 12. Using this rule, it will be 2 plus 1 times 1 plus 1, which will be 3 times 2, so 6 divisors, which is correct. If you look at this, so 1 plus 2, 3, 4, 5, 6, which, so this is correct. Okay, so let's look at a problem quickly. How many divisors will 1995 equal to 3 times 5 times 7 times 19 have? So this was also in an old SLAMO paper, I think. So what you'd notice, using the rule again, so 3 to the power of 1, 5 to the power of 1, 7 to the power of 1, 9 to the power of 1. So this will have 1 plus 1, 1 plus 1, 1 plus 1, and 1 plus 1 divisors, which is 16, so it will have 16 divisors. Okay. Next rule is for the infinitude of primes. So this rule states, or Euclid proved, that there exists infinitely many primes. I'm not going to do the proof now, but it is a very nice proof, and how it is done is you assume the opposite, in that you assume that there does exist a biggest prime, and then you show that there must be some contradiction because of this assumption. So yeah, you can go check out proof. Okay. Now we're going to do a problem using some of these rules that we've learned today. This problem was asked in 2019's camp. This says, find all positive integers n where the product of the positive factors of n is n to the power of 3. Okay, so how we're going to do this, let's try some small numbers first. So let's see, n equals 1. Let's write this. So divisors, this is n. This will be n to the power of 3. So say n was 1, divisors would only be 1, n to the power of 3 would be 1. This works. If n was 2, the divisors would be 1 and 2. N to the power of 3 would be 2 to the power of 3, so 8. this would not work since 1 plus 2 does not equal 8. If we had 3, it would be 1 and 3. This would be equal to 27. This would also not work since 1 times 3 does not equal 27. 4 is 1, 2, and 4. This is going to equal 64. This would also not work since 1 times 2 times 4 will equal 8. Okay. So now let's try to prove the question. I'm going to erase this. Okay, so we saw that n equals 1 was a solution. So note that n equals 1 is a solution. Okay, so let's take a divisor q and see what happens. So let's have let q be a divisor of n. So q divides n, and what we have is if q divides n, so q divides n implies that n over q will also divide n. So let's look at an example. Let's say n was 12 and q was 3. Then we could say n over q is going to be equal to 4, and 4 will also divide 12. So 3 will divide 12 and 4 will divide 12. Okay. Another thing we can note is if q is smaller than the square root of n, then n over q will be bigger or equal to the square root of n. If they are both bigger than the square root of n, then their product will be equaling n, will be too big. If they are both less than the square root of n, their product would be too small. So yeah, so let's look at an example quickly again. So 12, let's look at the divisors of 12. So 1, 2, 3, 4, 6, and 12. So square roots of 12 is going to be between 4 and 3. So say q was equal to 2, then n over q would be 6. So 2 is smaller than the square root of 12, and 6 is bigger than the square root of 12. So this works out. So you're kind of splitting the numbers down the middle, if you want to think about it like that. Okay. Now we're going to look at the case if n is a perfect square. Well, let's quickly, so from this, we can say that the factors are going to be in pairs. So you can say from 12, when we looked at 12, 3 and 4 will be together, 2 and 6 will be together. If n is a perfect square, so let's make n equals k squared for some k, part of the natural numbers. So then this means that k will not be in a pair. So will be dealt with separately. So now we're going to look at what the product of the pairs will be. So note that the product of a pair equals n. This means that product of all the pairs will be a multiple of n, or more specifically, n to the power of something. However, the question states that the product of the positive factors of n is supposed to be n to the power of 3. So it's supposed to be n to the power of something. So if we were to multiply k with all of these pairs, if we were to multiply k with all of these pairs, in other words, we're taking the product of the positive factors, taking the product of the positive factors, pairs, it would not be a multiple of n anymore. So this means, let's quickly look at an example first. Say we had 36. So 36 is equal to, or the prime divisors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. So if you look at their pairs, 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6 can be seen as k. Now 1 plus 36 is 36, 2 times 18 is 36, 3 times 12 is 36, 4 times 9 is 36, and if you multiply all of these pairs, they're going to be 36 to the power of 4. Now this 6 would disrupt this product, since it has to be a n to the power of something, or 36 to the power of something. So that's why we can now say n cannot be, so this implies n cannot be a perfect square. Okay, so now looking at the rule, so let's rewrite n as being equal to this again, p1 alpha 1, p2 alpha 2. So where the p's are where p1, p2, so pk are unique primes, and alpha 1, alpha 2, so alpha k, are integers, or not integers, natural numbers, sorry, just as the fundamental theorem of arithmetic states. Now we know this will have, if you write n as this, n will have not prime divisors. What we can also note is since the product of the pairs, so we know k, there can't be a k, so there can't be a k squared equals to n. Since product of pairs is going to be to equal n to the power of 3. This means there will be 3 pairs. In other words, there is going to be 6 divisors of n. So in other words, we know that this is going to equal 6. And from here we can see, since we know the alphas are supposed to be natural numbers, we can see that the solutions are, thus solutions six is either going to be equal to 2 times 3, or it is equal to just 6. In other words, it's going to be equal to 1 plus 1 times 2 plus 1, or it's equal to just 5 plus 1, which means either we have alpha 1 equal 1 and alpha 2 equal 2, or we have, so this is a statement, or we have alpha 1 equals 5, which means n is either equal to p1 to the power of 1 times p2 to the power of 2, or n is going to be p1 to the power of 5. So now what we have these two solutions, and we can check them quickly. So let's just write our solution along 1. Check solutions. So what we had was n equals 1, n equals p1, and n equals p1 to the power 5, where p1 and p2 are unique primes. So let's check that quickly. So if we have this, the second option, we have the factors being 1, p1, p2, p1, p2, p2 squared, and p1, p2 squared. And we can pair them together, 1 and p1, p2 squared, this with this, and this with this. There will be 3 pairs. If you multiply all the divisors together, you will get p1 to the power 3 times p2 to the power of 6, which will satisfy the condition. And if we have the third option, we have 1, p1, p1 squared, p1 to the power 3, p1 to the power 4, p1 to the power 5, and once again making pairs, these two together, these two together, these together, they would add up to, or they would multiply to get p1 to the power of 15. Okay, so that was the last problem. I hope you guys understood what I was saying, and I'll see you guys again tomorrow. Thank you.